does not make linear sense to...
Okay guys, today we're talking about graphing rational functions. We are actually going to start off immediately from the lab manual and work from the lab manual the whole time. This is the graphing rational functions section. All right, so the section starts off with a skill builder. Skill builder just basically meaning review. This is from our introduction to rational functions, right? This is asking us about all of the different properties that we learned about when we talked about rational functions initially. So let's go ahead and fill this out for this problem here. We've got, the first thing it asks us is the ordered pair of a whole, if it exists. How did we find a whole? Well, remember, wholes were kind of a bite that we took out of the function, right? The function had an open point just sort of in the middle of it. And it was just like a little bite that we took out of the domain, right? And those occurred when we had a repeated factor on the top and the bottom, right? A repeated factor in the numerator and denominator. So do we have that here? We do, right? We have x minus 1 and x minus 1. So, ordered pair of a whole, if we have x minus 1, it means we have an x value of 1 for the whole. And what did we do with that? Well, it's asking for the ordered pair, so we need x and y. So, how do we find y? The y value of a whole. The function looked exactly like, has the same exact shape as the function without those repeated factors, just with the whole in place, right? So we could use the function without the repeated factors, right? We called it f sub s or g sub s of x of whatever function we were talking about without the repeated factors, right? F simplified. So if we take out x minus 1, we're left with 3, x plus 3 over x minus 4. And when we plug in the x value, f sub s of 1, we get 3 times 1 plus 3 over 1 minus 4, which gives me 3 times 4 over negative 3, which is negative 4. So it looks like we have an ordered point of a whole, 1, negative 4. The next thing it's asking for are vertical asymptotes. Vertical asymptotes are also something that we take out of the domain of the function, right? Because we don't have a value of the function at the horizontal asymptote, right? The function is approaching infinity or negative infinity, and potentially both, kind of, on the opposite sides. So we take it out of our domain. Something that's going to be excluded from our domain is going to come from the denominator, right? It's where the denominator equals 0. So the two places where our denominator is 0 are x equals 4 from this factor and x equals 1 from this factor. But we know that x equals 1 is a whole, so it can't be a whole and a vertical asymptote. So 1 is not a vertical asymptote, and we're just left with x equals 4. And of course, since it's an asymptote, it's a line, and we need it to look like a line, so we have to write x equals with it as well. Equation of the horizontal asymptote. Okay, so how do we find horizontal asymptotes? Well, we did that by doing that long division, right? Which, when we did the long division, we wanted to divide the first term by the first term. And that told us that we needed to look at the degree, right? So let's refresh on our non-vertical asymptote rules. First, let's recall the case where we had a smaller degree on the top than on the bottom, right? The top was p of x because we were looking at the function p of x over d of x, right? Polynomial over denominator. When this was the case, we had a horizontal asymptote at y equals 0, right? Because since we had a larger degree on the bottom, we couldn't fit that function. We couldn't fit, if it was an x squared, we couldn't fit x squared into x, or if it was x cubed, we couldn't fit x cubed into x squared. So we end up with 0. If we had the same degree on the top and the bottom, we had a horizontal asymptote at y equals the leading coefficient of p of x over the leading coefficient of d of x. Right, because if we have the same degree, when we do that division, the long division of polynomials, we would divide the first term by first term. They would have the same degree, so the x terms would cancel, and we'd just be left with the leading coefficients. So we would divide them, we'd get a constant term, and that's what we would have. And the last case that we talked about, and these are all of the cases that we'll see for this class, last case we talked about was when we had the degree of the top, p of x, is exactly 1 larger than the degree of d of x. Right, so we have exactly 1 larger on top than on the bottom, and that left us with a slant asymptote that we could calculate by finding the quotient of p of x over d of x, and it would give us a line. Okay, so now that we've refreshed on all of those, let's go back to the problem here. We're looking for the horizontal asymptote here, if it exists. So let's think back to our rules. We need to look at the degrees of the top and the bottom. So the degree of p of x is what here? Well, we remember that the degree of a polynomial either is the exponent on the largest term, right, in standard form, when it's in standard form, or it's the number of roots that we have, number of factors. So here we're not in standard form, so let's count factors. It looks like we've got 2. So the degree of the top, p of x, is 2. Degree of d of x is the denominator. We also don't have this one in standard form either, so we need to count factors, and we have 2 here as well. So we have the same degree, which means that, thinking back to our rules, since we have the same degree, then we're going to have a horizontal asymptote at y equals the leading coefficient of the top over the leading coefficient of the bottom. Here that's 3 over 1, also known as 3. So we have an asymptote y equals 3. Do we have a slant asymptote? Well, so remember, we can't have a slant asymptote and a horizontal asymptote because both of them come from dividing the polynomials. So since we already got y equals 3, then we can't have a slant asymptote. So we can write does not exist here. If you're doing this in Desmos or WebAssign, it'll tell you exactly what it wants to see. It might say it wants you to write none or NA or DNE or whatever. Just make sure you're following what it's asking for. All right, next up we're looking for the x-intercepts. X-intercepts were, again, where we were intersecting the line y equals 0, right, the x-axis, which means that all the points on that line are going to have some value and then a y value of 0. So some value for x and then a y value of 0. So we need to find this x value. If the y value is 0, it means that f of x equals 0, which we talked about how with fractions, that's going to happen when the numerator is 0, right? In the last video, in the Introduction to Rational Functions video. So where the top is 0, we can figure out where the top is 0 by looking at the factors, right? Finding the roots. The two roots we have are positive 1 and negative 3. What do we know about positive 1 so far? Well, remember we had a hole at x equals positive 1. So since we have a hole there, that definitely can't also be an x-intercept. So our only x-intercept here is negative 3. Last but not least, y-intercept was very similar, right? But the x value is 0 because it's where we're intersecting x equals 0. Where x equals 0 is just f of 0, right? We're replacing x with 0. F of 0 is 3 times 0 minus 1 times 0 plus 3 over 0 minus 4 times 0 minus 1. We end up with negative 9 on top over positive 4, which is negative 2.25. Okay, so those are all of the properties that we've talked about so far. Today, of course, we're graphing rational functions, so we're going to use all of these facts to graph this rational function. So moving on down to this example 1, it's asking us to use all this stuff. The first step is to graph the vertical asymptotes. So where do we have vertical asymptotes? Looks like we have one at x equals positive 4. Positive 4 right here. Second step is to graph the horizontal or slant asymptote. We have a horizontal asymptote here at positive 3, and of course no slant asymptote because we have that horizontal asymptote. Plot the hole if it exists. We discovered that our hole was at positive 1, negative 4, so that's right here. We draw the open point. It's asking us to plot the x-intercepts. We have an x-intercept at negative 3, 0. That's right there. We have a y-intercept at 0, negative 2.25, so that's a little bit lower than negative 2. And graph an additional point or two to get the basic shape. So, all right, let's think about this. This is the first new thing we've talked about. So we know that we have these asymptotes, so we need to approach but not touch them, right, as we move off the graph. That means we need to get really close to this guy, right, and really close to this guy. So we have a few options for how this might look, right? We could either have this shape, this shape, this shape, or this shape with these asymptotes that are splitting it up. How do we know whether we're approaching this side or up here or, which one we're dealing with? Well, we know that we've got these points here that we have to pass through. So since we have to pass through these points, this part of the graph is gonna look like this, right? That's for sure. So that's good. We know that because of the vertical line test, we're not gonna have another piece of the graph up here, right? So the only possible places for our graph to be are here or here. It's not going to be both, it's going to be one, right, for the same reason, because of that vertical line test. So let's figure out whether we have this shape on top or this shape underneath. How can we do that? Well, we can graph a point at one of these x values to the right side of this asymptote. This asymptote is at +4, so we just need to pick a number that's greater than 4. Okay, I made a mistake working this out the first time, so I'm going to try x equals 8 here. If I plug in 8 into f of x, I'm looking for f of 8. I've got 3 times 8 minus 1 times 8 plus 3 times 8 minus 4 times 8 minus 1. So on top I have 3 times 7 times 8 plus 3 is 11 divided by 4 times 7. So those 7s are going to cancel. I'm left with 3 times 11, which is 33, divided by 4. 33 divided by 4 is 8.25. So that means the point 8.25, is on the graph of my function. So 8, 1, 2, 3, 4, 5, 6, 7, 8.25, so a little bit above 8. And our function is going to look like this. I drew it off the side, but you guys get the point, right? We're going to be approaching that line and this line. So because we have this point up here, that curve of our function is going to be on top, not underneath, right? So we have this shape. Right, so we kind of narrowed it down. We knew that we had this portion of this sort of lower left quadrant in there, so we needed to know whether we had the right half of the graph was on top or underneath. Turns out it was on top, so we have this shape, and that's what we ended up with. Let's try another one. Okay, let's start with number 2 here. So we're given this function, f of x. We're asked to state the relevant information and then graph. We're not told exactly what the relevant information is, so we need to kind of keep that stuff in mind. So the first thing that's coming in mind for us to look for me, is holes. Do we have a hole here? How did we find holes? It was the repeated factors, right? So if we had a repeated factor in the numerator and the denominator, right, the same factor, then that would give us a hole. We don't have that here, so we have none of those, DNE. All right, what about vertical asymptotes? Well, those came from the factors of the denominator that weren't holes. So what are the factors of our denominator? X plus 2. So we have an x-intercept at x equals -2. Since it's a line, we definitely need to include x equals. Let's think about horizontal asymptote. So that required us to look at our degrees of the two polynomials, the one on top and the bottom. So our degree on top is 2 because we have 2 factors. Our degree underneath is 1 because we have 1 factor. That means we have a degree of 1 larger on the top than on the bottom. What does that mean we have? It means we have a slant asymptote, right? And if we have a slant asymptote, then we don't have a horizontal asymptote. So DNE for horizontal asymptote. Going ahead and jumping straight into the slant asymptote, how did we calculate that? We calculated it by doing the polynomial long division, right? So in order for us to do the polynomial long division, we need the polynomials, which means we're going to have to factor this, which requires us to have them both in standard form, which means we need to FOIL this out. So 3 times x plus 3 times x plus 1 gives us 3 times, we FOIL, we get x squared plus 4x plus 3. When we distribute that 3, we get 3x squared plus 12x plus 9. We can set up our polynomial long division. We have x plus 2 dividing 3x squared plus 12x plus 9. We divide first term by first term starting out. That's 3x squared over x, which gives us 3x. We multiply by our divisor. We get 3x squared plus 6x, and we subtract it all. 3x squared minus 3x squared is 0. 12x minus 6x is 6x. We bring down the 9. We divide first term by first term again. The x's cancel. We're left with 6. So we get 3x plus 6 as our quotient, which means we have a slant asymptote at y equals 3x plus 6. And of course, I made a mistake. We have to include that y equals in our answer as well because it's an equation. So y equals 3x plus 6. Last but not least, we need to find any intercepts if they exist. So x-intercept, those guys come from the top, right? The numerator, the factors of the numerator that are not whole, that don't give us a whole. So that's x plus 3 and x plus 1. So we get -3 and -1. Of course, we need to write them in coordinate point form. So we get -3, 0 and -1, 0. Y-intercept, again, that's where x equals 0, right? So we're just looking for f of 0. We get 3 times 0 plus 3 times 0 plus 1 over 0 plus 2. So we get 9 over 2, or 4.5, giving us a coordinate point of 0, 4.5. Okay, so we have a bunch of stuff that we need to graph. Let's go ahead and give that a shot. So let's start out with this vertical asymptote. We've got a vertical asymptote at x equals -2. That's right there. We don't have a horizontal asymptote, or any holes for that matter, but we do have a slant asymptote at 3x plus 6. How do we graph that line, 3x plus 6? Well, it's a line that has a y-intercept of 6, right? So it passes through this point right here. It also has a slope of 3, so that means we move over 1 and up 3 each time. So starting here, over 1, down 3 over 1, down 3 over 1, down 3 over 1, down 3 over 1, all the way, and we can draw that dotted line because this is our slant asymptote. Now we have our two x-intercepts, one at -3, 0, and one at -1, 0. Now, again, we have a similar situation where we need to figure out whether our graph is right here on top, or in this little sliver, or in this sliver, or in this sliver, right? Where is our graph occupying, right? What section here is it in? Well, it's pretty easy to see here where we have it, right? Because we have these points graphed already, right? So if we have a point here, it means we have to be in this section of the coordinate plane, right? So we approach this vertical vertical asymptote, and we approach right here this slant asymptote. Similarly here, we're approaching, right, this vertical asymptote and this slant asymptote. So our graph looks like this. It's kind of a skinny graph. That's fine. Oops, I forgot to graph the y-intercept. So we definitely want to make sure we graph all this stuff before we start, but turns out we were right? It passes through right at 4.5. We have that y-intercept right at 4.5. So just a confirmation that we were totally correct. So that's the graph of number 2. Let's do one last problem. Number 3. So we're given this function f of x. Let's start by looking for any holes. So remember, holes are where we have repeated factors in the numerator and denominator. Do we have that this time? We do, right? We have x minus 1 and x minus 1 both on top and underneath. So we have a hole at x equals 1. How do we find the y value of the hole? Well, we simplify, right? We remove those repeated factors and we plug into what's left. So, right, simplified function we call f sub s of x. We just remove these functions. When I remove it from the top, I'm left with 1. Right, if I cancel out a factor here, I would be left with 1. So we have 1 on top over the x plus 2 is left underneath. So f sub s of 1 is 1 over 1 plus 2, which gives us 1/3, meaning we have a hole at 1 and 1/3. Okay, vertical asymptotes. Well, remember, those are something that's going to restrict our domain. Stuff that restricts our domain comes from the denominator. So in the denominator, we have x minus 1 and x plus 2, but we know that x minus 1 gave us a hole, so we're only dealing with x plus 2. So that means we have a vertical asymptote at x equals -2. Horizontal asymptote, we've got to think about our rules, which means we need to think about our degree. The degree on top is smaller than the degree on the bottom, which means that when we do that division, right, when we divide, looking for the quotient of that fraction of the, division that's given by the fraction problem of this rational function, it's not going to fit, right? We're going to be trying to fit an x squared term into an x term, and it's not going to work, right? So that means we have a horizontal asymptote of y equals 0. Since we have a horizontal asymptote, it means we don't have a slant asymptote because we can only have one. So DNE. All right, x and y intercepts. Do we have any? Let's see. So x-intercepts come from the factors of the top that don't give us holes. And our only factor on top gave us a hole, right? So there's nothing on top left that will make the function 0. So since there's no x values that will give us a value of 0, then there are no x-intercepts. No x-intercepts. Y-intercepts? Let's figure it out. Well, y-intercepts were where we had an x value of 0, right? It's where we intersect the y-axis, which is the line x equals 0. So that's f of 0, right? So that gives us 0 minus 1 over 0 minus 1 times 0 plus 2. So -1 over -2, or positive 0.5. So we have a y-intercept at 0.5. All of these values, right, are pretty small. We have 1, 1/3, -2, 0, and 1/2. So in order to sort of really see what's going on here, I'm going to make our axis a little bit bigger. So instead of each grid line representing 1, I'm going to let 2 represent 1. 3, 4, same thing here. 1, 2, 3, 4. Okay, let's start graphing stuff. So we have the whole at 1 and 1/3. So 1 and 1/3 from here would look like this probably. We have the open point. Next we have x equals -2, the vertical asymptote. So -2 would be right here. Then we have the horizontal asymptote at y equals 0. Since this line is so thick, I'm going to draw this as sort of some slashed lines because we wouldn't really be able to see dotted lines otherwise running through that. And last but not least, we have the y-intercept at 0.5. So that is right here. Okay, so now we need to figure out whether our graph is in this quadrant or this quadrant, and also whether our graph is in this quadrant or this quadrant. On the right side of the vertical asymptote, it's pretty easy because we already know that these points are here and we have to pass through these points. So we've definitely got this sort of shape going on. We want to get really, really close to this vertical asymptote, really close to this horizontal asymptote. Now we need to figure out whether we're on top over here or underneath. We can do that by simply picking a point on this side and figuring out what it's equal to. I'm going to choose maybe right here. And of course, remember each of our grid lines is 1/2. So this is -3. So I'm going to plug -3 into the function for x. So f of -3 gives me -3 minus 1 over -3 minus 1 times -3 plus 2. That gives me -4 over -4 times -1. -4 over -4 is gonna, right, kind of 0, is gonna kind of cancel. And then we divide by -1, so we have -1. This means we have the point -3, -1 on the graph. So -3, -1 is right here. Since this point is underneath, I know that my graph is going to look like this because I have to approach that horizontal asymptote and this negative asymptote and this vertical asymptote as well. Okay, that's all I have for y'all for graphing rational functions. Hopefully it's making sense. It is a lot of practice with our properties of rational functions from last time, so we still get to kind of review on that stuff as well. And hopefully it's making sense. All right, thanks y'all.